Hello, everybody, again. It is a place for me to introduce the professor Ewa Drgas-Burchardt, sorry for the pronunciation, from Poland. She will talk about consecutive coloring of oriented graph. But I am not going to talk about Ewa's academic work. It will be too long. I want to tell you about my friend Ewa. I met Ewa in 2009 in CID, Coloring, Independence and Domination Conference in Skarska Poreva. Ewa was very sweet and kind person. I have opportunity to share with Ewa many conferences, long conversations, and I visit her university 3 or 4 years ago, where I passed very, very nice time with Ewa and the other professor of the university. So I hope that very soon Ewa can visit my house at my university in Mexico. Thanks, Ewa.
Thank you, Rita. Thank you for introduction. Thank you for invitation. Also, thank all of you for being with me. Maybe let us start with sharing my screen. One minute more. I hope my screen is visible.
We can see your screen and hear you completely well.
Once again, I don't hear you.
We can see your screen and hear you perfectly fine.
Okay, thank you. Let us start with the topic, which is very interesting for me, and I hope it will be also interesting for you. Especially after my talk. The aim of this talk is the presentation of some problems that, in my opinion, may be solved by students. This is the idea of my talk, to present some problems that are simply presentable, but of course necessarily simply solvable. Let us start with a plan. Plan is the following. I'm going to divide my talk into 2 parts. In the first one, I'm going to present some basic definitions and motivation connected with the problem of consecutive coloring of graphs. Next, some known results, but only those ones that will be needed to present problems. Next, problems in this area. And next, I'm going to move to the second part, which will be connected with consecutive colorability of oriented graphs. In this part, also basic definitions will be presented and some connections between the first subtopic with the second one. Let us start with motivation, which is always given the same, but we have the set of students and also the set of teachers, and they have planned some lessons, some individual lessons, which can be modeled by such a graph in which the set of vertices is the set of students and teachers, and the edge between the student and the teacher means that this teacher will be conducted the lesson in which this student has to attend. Our goal is the construction of the schedule of these lessons, assuming that all the lessons must be planned in the same day. But our schedule must be planned in such a way that, first of all, every person must attend in lessons that are planned for him, for her. And moreover, we need have no breaks in lessons. In the graph theory language, we can do about the coloring of edges of our graph in colors, which will be integers. I associated with color blue the integer 1 with the color red integer 2 and so on. In such a way that for every vertex, edges that are incident with this vertex must be different, because the pieces of time in which these lessons are planned must be different. And moreover, the colors that are put on the edges that are incident with a vertex must create an interval of integers, because we have to have no breaks. This is the idea of such a coloring, which in a formal way can be defined in the following way. A consecutive coloring of a graph G is a proper edge coloring. Proper means that colors incident with each vertex must be different. This is a proper edge coloring of this graph with integers in such a way that the colors of edges incident with each vertex form an interval of integers. This definition was introduced by two Armenian mathematicians, Asreat and Kamalian, in 1987. A graph for which such a coloring exists is called consecutively colorable. By the motivation, graphs that we should consider are bipartite. What does it mean to be a bipartite? To be a bipartite means that in such a graph, there is a partition of its vertex set into two parts. Here we have such two parts, such that every edge of this graph joins a vertex from one of the partition parts with the vertex from another one. This is the definition of to be bipartite. But Ishtok taught us also that every bipartite graph has a chromatic number equal to 2. And moreover, this is the characteristic of such a graph. Also, Ishtok taught us that graphs that have chromatic number equal to 2, which means that are bipartite, do not contain any cycle of odd length. Here we have an example of a graph which is not bipartite. Why? Because it contains as a subgraph a cycle of length 3. 3 is an odd number. During this talk also I try to focus on the class of graphs which is called forest. Forest is a graph which does not contain any cycle. Here is an example of a graph which does not contain any cycle, which means this is a forest. But if a graph additionally is connected means that for any two vertices of this graph, there is a path that joins these two vertices. For instance, if we look at these two vertices, there is a path joining them. Such a graph is connected. Once again, if it is connected and without cycles, such a graph is called a tree. Here is an example of a tree. Here also is a tree because here is a graph which is connected for sure, and moreover does not contain any cycle. I would like to say that every forest is a bipartite graph. The bipartition here is presented by two coloring we know that if a graph is too colorable, it is bipartite. As I mentioned, the definition of consecutive coloring was first introduced for bipartite graph because of the motivation, but in the same paper, Asratian and Kamalian extended this definition to non-bipartite graphs. Here is an example of such a graph, which is not bipartite because it has a cycle of length 3. And here is also an example of a coloring, which is consecutive. Why? Because for every vertex, colors that we used are edges incident with this vertex that we used are different, and moreover, they form an interval of integers, which means the colors are consecutive. Here we have colors 2 and 3, here 1 and 2, here 1, 2, 3, and for this vertex 2. This coloring is consecutive. Let us observe that such a graph is not consecutively colorable. Why? If we try to color this graph consecutively, we must put, with respect to this vertex, for these two edges, different consecutive colors. No matter which one, for instance, 1 and 2. But if we put 1 and 2 here, with respect to this vertex, this edge must obtain color 1 or 3, if such a coloring exists. With respect to this vertex, 0 or 2. Because we have no common colors analyzed with respect to this vertex and this vertex that we can put on this edge, such a coloring does not exist. In general, deciding whether a graph G is consecutively colorable is an NP-complete problem. It was proved in this first paper by these two mathematicians, but also next, Sebastianov proved in 1990 that this problem still is NP-complete if we consider a class of bipartite graphs. This result was for all graphs, for the class of all graphs, and Sebastianov proved this result for bipartite graphs. Now I would like to put some results about consecutive colorability of graphs. Especially, I would like to list some classes of graphs that are consecutively colorable, but only those ones which will be needed in the remaining part of my talk. Complete graphs of even order are consecutively colorable, unlike to complete graphs on odd order. Complete bipartite graphs are also consecutively colorable. All forests are also consecutively colorable. Bipartite graphs that are subcubic. Subcubic means that the maximum degree of such a graph is not greater than 3. Regular and bipartite graphs, and bipartite graphs that have at most 15 vertices. Here we have all bipartite graphs that have at most 15 vertices. On the other hand, there is a graph with 19 vertices, which is presented here, which is bipartite. I colored the vertices of this graph with 2 colors, which means such a graph is bipartite, which is not consecutively colorable. This graph is not consecutively colorable. It was discovered by this person in 1989, but this result was unpublished. In 1999, sorry, 89 was here. In 1999, Małafieński published this result. It follows that we have first problem that I am tried to present. Whether or not there is a bipartite graph having maybe 16, maybe 17, maybe 18 vertices that is not consecutively colorable. I would like to recall that we know graphs which smaller than 19 number of vertices which are not consecutively colorable. We had an example, a triangle, for instance, but this graph is not bipartite. Among bipartite graphs, all graphs with at most 15 vertices are consecutively colorable. 19 vertices is enough to find the graph which is not consecutively colorable and bipartite. What about this interval? This is my first question. This question was posed in 2013 and there is no progress in the solution. Maybe you can find the solution of this problem. To present the second problem, I would like to introduce some notation. This notation will be connected with a tree. Let us start with a tree T. And by L of T, I would like to denote the set of, not the set, but the number of leaves of this tree, which means the number of vertices of degree 1 in a tree. And by M of T, I will denote the largest possible number of edges in a caterpillar of this tree. What does it mean to be a caterpillar of a tree? First, I define the caterpillar. The caterpillar is a tree in which we have a main path and attached edges, the edges that are attached to this main path. This is a caterpillar, and the caterpillar is a caterpillar of a tree if such a caterpillar is a subgraph of our tree. Consider an example. Here is our tree, which was presented before. Here are colored all the leaves of this tree. And now I would like to find these two parameters, the number of leaves. The number of leaves can be found very quickly, and the number M of T, which means the largest possible number of edges in the caterpillar of this tree. If we start with this path and consider a caterpillar with largest possible number of edges with such a main path, then we can obtain 8 edges. This number, the good number, is the largest possible number of edges in the caterpillar of this tree? The answer is not, because we can find another caterpillar which with the main path given here and some attached edges, which has 10 edges. 10 is the best possible number, the largest possible number of edges in the caterpillar of this tree. What does it mean? Now I would like to present some construction. Construction connected with a tree. We have a tree. We put some additional vertex, separates additional vertex, and we join this vertex with all the leaves of our tree. If we started with a tree T, by T tilde, we denote such a graph constructed in this way. And we have the following theorem, which was proved by Petrosian and Khachatryan in 2014. If T is a tree, very special, which means such a tree in which the distance between any two leaves is an even number. The distance between two vertices is the number of edges in the shortest path joining these vertices. Because in a tree we have only one path that joins two vertices, this distance is simply speaking the number of edges in a path joining such a vertices. Once again, if T is a tree in which the distance between any two leaves is an even number, and moreover, if the number of leaves of this tree is greater than the largest possible number of edges in a caterpillar of this tree plus 2, then the graph T tilde constructed, as I mentioned before, is not consecutively colorable. This theorem was proved in this year. We cannot apply this theorem for our tree. Why? Because, for instance, these two vertices, this one and this one, are in distance 5, which means this tree does not satisfy one of our conditions. But we can do it for such a tree, and especially for such a graph obtained from this tree. Why? In this tree, the distance between any two leaves is an even number. If we have two leaves from different branches of this tree, here we have three symmetrical branches of this tree, and if we have leaves from different branches, the distance is 4. 4 is an even number. If we have two leaves from the same branch, the distance is 2. 2 is also an even number. Moreover, the number of leaves of this tree is 18. We can calculate it. The number of edges, the largest possible number of edges in a caterpillar of this tree is 15. Here is such a caterpillar. We can check it very quickly. And if we look at this inequality is satisfied. The number of leaves is greater than the largest possible number of edges in a caterpillar of this tree plus 2. It follows that such a graph constructed in steps as I presented is not consecutively colorable. And the question is whether or not this condition is also necessary, not only sufficient, but also necessary. In other words, and this is a conjecture, although this is a conjecture, in other words, the conjecture says that if T is a tree in which the distance between any two leaves is an even number, and this inequality holds, the opposite inequality to the previous one, then the graph which we constructed, the graph T tilde, the graph obtained from our tree by adding some new vertex and joining this vertex with all the leaves of this tree, is consecutively colorable. This is a conjecture, and I hope maybe you solve will solve the conjecture in the future. We know that such a graph is not consecutively colorable, but we can divide the set of edges of this graph here into blue and black edges in such a way that graphs induced by these edges, here I present the graph induced by black edges in this graph, and here I present the graph induced by blue edges in this graph. Both these graphs are consecutively colorable. Why they are consecutively colorable? Because they are trees. Every forest is consecutively colorable. This result was presented at one of my beginning slides. And there is a conjecture, which is my third problem, conjecture posed by Maria Aksanovich in 2013, that for each graph, there is a partition of its edges into two parts so that both graphs induced by partition parts are consecutively colorable. It's true for graphs that are consecutively colorable because we can partite the set of edges into empty set and the set of all edges of the graph. But for graphs that are not consecutively colorable, this is a conjecture, which is satisfied, of course, for this graph. Okay, now I'm going to the second part of my talk, which means consecutive colorability of oriented graphs. What does it mean to be an oriented graph? Here is a graph, and we can obtain from such a graph an oriented graph when we put directions on all the edges of this graph. Put direction means we say this vertex of this edge is the first vertex of this edge, and this one is the last vertex of this edge, and instead of edge we obtain an arc. Here is an oriented graph. If we start from an oriented graph, from such a graph, for example, and we remove orientations of its arc, we obtain a graph which is called an underlying graph of this oriented graph. From oriented graph to this graph, we obtain an underlying graph of this oriented graph. From this graph, by orientations of its edges, we obtain an oriented graph. And we define a consecutive coloring of oriented graphs similarly to the consecutive coloring of graphs with some exceptions. Namely, we require that for each vertex, the colors that we used for out arcs of this vertex must be different and must create an interval of integers, and the same for all in arcs that are incident with this vertex. I would like to say that this coloring is not consecutive. It is so because, for instance, in this vertex, we have in arcs, two in arcs. They are different, which is good, but the colors that we use are not consecutive. We have a gap between 1 and 3, which means that such a coloring is not consecutive. But we can improve this coloring, and we observe that this coloring satisfies this condition for every vertex, for this vertex, and also for this, and so on. Formally, let D be an oriented graph. A consecutive coloring of an oriented graph D is a mapping from an arc set of this oriented graph into the set of integers, such that for every vertex U of this oriented graph and all out neighbors of this vertex, the values, the colors of out arcs of this vertex are pairwise different and form an interval of integers, and the same for in arcs, which means for every vertex U of this oriented graph and all inner neighbors of this vertex, the values, the colors of in arcs associated adjacent to this vertex are pairwise different and form an interval of integers. As before, an oriented graph that has such a coloring is called consecutively colorable. My first and favorite problem, which is also the conjecture connected with this topic, was posed 3 years ago, but published in this year, and says that for each graph, for every graph, there is an orientation of its edges so that the resulting oriented graph is consecutively colorable. We confirmed this conjecture for some classes of oriented graphs, because we must orient these graphs in the future. But I would like to omit enumeration of such classes. Instead of this, I propose to give some words about connections between consecutive colorability of oriented graphs and consecutive colorability of graphs, especially consecutive colorability of oriented graph D and its underlying graph G of D. I recall that the underlying graph of an oriented graph D is a graph obtained by removing directions of arcs. This is the question, whether or not there exists such a connection between these two kinds of colorability, two kinds of objects. And the answer is there is no such connection. Why? First of all, each directed cycle, here is an example of a directed cycle, is consecutively colorable. Why? It is so because for each vertex of such a cycle, we have only one out arc incident with this vertex and only one in arc incident with this vertex, which means that no matter how we color the arcs of such an oriented graph, such a coloring will be consecutive. On the other hand, we know that the underlying graph of this oriented cycle is not consecutively colorable. We discussed this fact some slides ago. And more general, we know that cycles of odd order are not consecutively colorable. It was proved by Giaro, Kubala, and Małafiejski in 2004, which means that there is an infinite family of oriented graphs. I think about directed cycles of odd order such that they are consecutively colorable and their underlying graphs are not consecutively colorable because of this result. On the other hand, there are examples of oriented graphs that are not consecutively colorable, whose underlying graphs are consecutively colorable. Such a family, we can also find an infinite family of such graphs, but I would like to present only one example because the presentation of this family will be more complicated. This oriented graph, I will prove that it is not consecutively colorable, but its underlying graph is consecutively colorable. It is visible here because I present a consecutive coloring of this underlying graph. To observe that this oriented graph is not consecutively colorable, we must introduce some new notion. Namely, for an oriented graph D, we define a graph, which is not an underlying graph. This is completely different graph label it by this oriented graph D, which is constructed in the following way. First, we substitute each vertex of this oriented graph with two vertices, the vertex V with vertices V plus V minus, and we join two vertices of this new graph, U plus V minus, in this graph if and only if there is an arc from U to V in an oriented graph D. Consider an example. Here we have an oriented graph on 4 vertices, which means that our graph G up star for this oriented graph, which is presented here, must have 8 vertices, twice the number of vertices of this oriented graph, which means 8 in this case. And moreover, for each arc of this oriented graph, we can construct an edge in this graph. For instance, for this arc from V1, V4 to V4, we obtain the edge from V1 plus to V4 minus. Of course, there is a bijection between the set of edges of this graph and the set of arcs of this oriented graph. Moreover, we observe that if D is an oriented graph, then D is consecutively colorable if and only if this graph, which was constructed just before this slide, is consecutively colorable. Observe that these two kinds of consecutive colorability are different. Here is we say about consecutive colorability of oriented graph. Here on consecutive colorability of this graph. We come back to our example. We tried to prove that this oriented graph is not consecutively colorable. Instead of this, we can prove that such a graph is not consecutively colorable because of our result. Because this graph was constructed, used our construction, our 2 steps of the construction. And if we remove from this graph all isolated vertices, we obtain a graph which is known in the literature as Sebastianov graph, because Sebastianov proved in 1999 that such a graph is not consecutively colorable. It means that our oriented graph also is not consecutively colorable. Using the same theorem, theorem which gives us the reduction of the problem of consecutive colorability of oriented graphs to consecutive colorability of some special graph, we prove that deciding whether an oriented graph, here the letter D will be better, is consecutively colorable is an NP-complete problem. And finally, I would like to back to problems that I presented some slides ago. It was the problem 4. Problem 4, which says that for each graph there is an orientation of its edges so that the resulting oriented graph is consecutively colorable. And also, I would like back to the problem 3. Problem 3 taught us that for each graph, it was the conjecture that for each graph there is a partition of its edges into two parts so that both graphs induced by partition parts are consecutively colorable. It was a conjecture concerning graphs. It was a conjecture concerning, in some sense, graphs, in some sense, oriented graphs. And we proved that in the class of bipartite graphs, these two conjectures are equivalent, are the same. If you prove one of them, at the same time, we prove the second one, but only in the class of bipartite graphs. What about non-bipartite graphs? This is my 5 and the last question. What is the relationship between these two conjectures for non-bipartite graphs? Whether or not one of them implies a second one. Maybe none of them implies the second one. And finally, I would like to put references. There are many papers connected with this topic. I only the first, which was introduced the definition on consecutive colorability of graphs. It was named in this first paper interval coloring, not consecutive, but interval coloring. And this is the first paper in which consecutive colorability of oriented graphs was mentioned. Thank you for your attention. It's all.
Thank you very much, Ewa. I don't know if very nice talk.
Thank you.
I think it's special for our students. So I don't know if somebody has any question.
If you will some progress in the solution of my problems, please let me know. I am very interested in the solutions.
Yes, of course. We hope. We have a comment of Magda de Tlaf and Julian Fresan. They say that very nice talk. Norma Diez Marina say that it was excellent talk. Very interesting problems. Night says thank you, Ewa, excellent talk too. Vinicio Gomez, thank you. So I don't know if we have any question. We wait a little because our session in Facebook is a little late, some minutes or something. So Julian told us if we have any question. No questions in YouTube for now.
Maybe in the future.
Maybe in the future we will write you and say you if we have questions. Laura says thank you to both speakers. So I think I would like to say thank you for the speaker in live of today, Istok and Ewa. A very nice talk. And now I will give the Julian have information for us.
Thank you, Ewa. It was a really nice talk. And well, today we will have 3 works that will be in a moment, will appear on Facebook and on YouTube. These works are from Renata Zakreska. I hope I said it okay. Line random numbers for some graphs. From María del Rocío Sánchez López, enviando mensajes sin interferencia. And from Natalia Danieluk, select applications of machine learning in astronomy. Those will appear in a few moments in our YouTube channel and our Facebook page. Don't forget to subscribe to get the notifications of these works. And those will be the works of this day.
So, thank you very much, everybody. See you tomorrow. Remember, 10 a.m. in Mexico and 5 p.m. in Poland and the rest of Europe. Thank you very much.
Thank you a lot.
Thank
Bye.
you.